4.5 billion years, 400 million years of complex life, 150 million years of dinosaurs, 300 years of human industry. We take it for granted that we are the first civilization this planet has ever produced. But what if that assumption is mistaken? What if Earth has lived through this exact chapter once before and simply lost the memory of it? Chapter 1. The question nobody in science thought to ask. Before we begin, please take a moment to subscribe. And if you find yourself drawn into these videos, a like would mean a great deal. Now let us begin properly. Picture yourself standing on a beach at night. The waves are black, rolling beneath a sky thick with stars. You reach down and gather a handful of sand, letting it drain slowly between your fingers. Every single grain is a moment in time. Every grain a year, a century, 1,000 years. The sand cupped in your palm represents the last 10,000 years of human experience. The beach stretching away behind you into the darkness represents the 4.5 billion years that unfolded before. And somewhere out there, buried beneath layers of time so deep they resist the imagination, a question is waiting. What if we were not the first? It sounds like something lifted from a science fiction novel. It sounds like the opening act of a Hollywood film rather than a topic fit for academic discussion. And yet, in the year 2018, two respected researchers published a paper in the International Journal of Astrobiology that posed exactly this question, not as idle fantasy, not as speculation, but as a carefully constructed thought experiment designed to test the outer boundaries of what science can actually know about the deep history of our world. Astrophysicist Adam Frank of the University of Rochester, along with climate scientist Gavin Schmidt of NASA's Goddard Institute for Space Studies, posed a question that was deceptively plain. If an industrial civilization had existed on Earth tens or hundreds of millions of years before our own, would we even possess the tools to detect it? They named their inquiry the Silurian Hypothesis. The name is a reference to a fictional race from the long-running British television series Doctor Who, a race of intelligent reptiles supposedly responsible for a forgotten ancient civilization that flourished on Earth before the rise of mammals. The two scientists were not suggesting that such beings actually existed. They were raising something far more profound. They were asking whether our certainty about being the only civilization in Earth's long history rests on actual evidence or merely on comfortable assumption. Sit with that for a moment. We assume we are the first. We assume that across 4.5 billion years of planetary history, across hundreds of millions of years of complex life, we are the sole species ever to have developed technology, constructed cities, and reshaped the surface of this world. We assume it because no one has ever produced a clear artifact, a recognizable ruin, or any unmistakable sign of someone who came before. But the absence of evidence is not evidence of absence, especially not when you truly grasp what the Earth does to evidence over the course of deep time. Complex life has existed on this world for at least 400 million years. Land animals have walked the continents for nearly as long. The dinosaurs held their dominion for more than 150 million years. Our own species, Homo sapiens, has walked this planet for roughly 300,000 years. And our industrial civilization, the one responsible for factories and generating stations and satellites and cities visible from orbit, is just about 300 years old. 300 years out of 400 million. If you were to compress the entirety of complex Earth history into a single calendar year, the whole of our industrial existence would occupy less than 60 seconds before midnight on December the 31st. Everything we have ever made, everything we believe we know, every machine, every monument, every shred of evidence that we were ever here, would all squeeze into that final slice of time. Now stop and ask yourself something. If another civilization had risen and collapsed somewhere inside that immense span, a civilization that endured for 1,000 years, or 10,000, or perhaps even 100,000, how much of it would still remain? What could possibly survive millions of years of erosion, burial, subduction beneath tectonic plates, and transformation under heat and pressure? The uncomfortable, honest answer is almost nothing at all. We will explore exactly why in the chapters that follow. We will examine what becomes of evidence across geological time. We will look at the strange anomalies that haunt Earth's deep past, anomalies that scientists still struggle to explain in full. We will consider the myths and legends that echo through cultures separated by vast oceans. stories of lost civilizations and ancient catastrophes that seem too widespread to dismiss as mere accident. And we will face the unsettling reality of what our own civilization will appear to be in the eyes of whoever or whatever might stumble upon our remains millions of years from now. But first, we need to understand why this question even matters. Why would trained scientists invest their time and professional reputation in what looks at first glance like an absurd premise? The answer lies in what the thought experiment reveals about us. Frank and Schmidt were not attempting to prove that dinosaurs operated nuclear power plants or that intelligent reptiles once ruled the planet. They were trying to map the limits of detection itself. They wanted to know what traces an industrial civilization would leave behind in the geological record and how long those traces could possibly endure. And the results of their inquiry carry implications that stretch far beyond our own world. We are currently looking for signs of life on other planets. We scan the atmospheres of distant exoplanets for chemical signatures that might reveal biological activity. We dream of intercepting radio broadcasts from alien civilizations. We send probes to the surface of Mars hunting for microbes. But all of this presupposes that we understand what evidence of a past civilization ought to look like. All of it assumes we know what we are searching for. The Silurian Hypothesis confronts us with an uncomfortable possibility. If we cannot reliably detect a previous civilization on our own planet, the one we have studied most thoroughly, how can we place any real confidence in detecting one somewhere far away? Think about what we know regarding fossilization. The process by which organic remains become locked in stone is extraordinarily uncommon. Only a vanishingly tiny slice of every organism that ever lived leaves any mark in the fossil record at all. The conditions have to line up with remarkable precision. Remains must be buried quickly, shielded from scavengers and rot, and subjected to exactly the right chemical and physical processes that convert organic tissue into mineral. Most creatures that die simply decay and disappear without a whisper. Now apply that truth to civilization itself. Human beings have existed in our current anatomical form for 300,000 years. For nearly all of that time, we lived as hunter-gatherers in small roving bands. We left almost nothing behind. No cities, no monuments, no permanent architecture of any kind. Even our own bones are shockingly scarce in the fossil record. If you were hunting for direct physical evidence of humans from 100,000 years ago, you would be combing for isolated fragments. A stray tooth somewhere. A piece of skull somewhere else. Scattered across entire continents and buried under meters of sediment. Now carry that logic backward millions of years. The oldest exposed surface on Earth sits in Israel's Negev desert, and it is only about 1 million years old. Everything else has been buried, eroded, drawn beneath tectonic plates, or cooked and squeezed by heat and pressure into something unrecognizable. The crust of the Earth is not a museum, it is a recycling plant. Continental plates plunge into the mantle and melt. Mountains heave upward and then crumble. Rivers carve through solid stone and carry the fragments out to sea. Nothing on the surface lasts. Less than 3% of Earth's surface today is urban. The entire footprint of human civilization occupies only a small fraction of the planet. Project that forward 1 million years. What would remain of us? Our cities would lie buried under sediment or ground into powder by glaciers. Our monuments would dissolve under acid rain or collapse under their own weight. Even our most enduring structures, the ones built from stone and concrete and steel, would surrender to the relentless grinding of geological forces. The only traces that might still persist would be chemical signatures locked into sediment, anomalies in ratios of carbon isotopes, strange concentrations of heavy metals, spikes in radioactive elements. Evidence not of the civilization itself, but of the way it disturbed its environment. And this is precisely where the thought experiment becomes genuinely unsettling. Because we have already found such anomalies in the geological record. Events written into Earth's past that look eerily similar to the effects we are currently having on the planet. Around 56 million years ago, something peculiar happened. Over what was, in geological terms, a remarkably short window, perhaps just a few thousand years, vast quantities of carbon surged into the atmosphere. Global temperatures climbed by 5 to 8 degrees Celsius. The oceans turned acidic. Species went extinct. The event bears the name Paleocene-Eocene thermal maximum, and scientists continue to argue about what actually caused it. The leading theories involve volcanic activity, or the sudden release of methane trapped in ocean sediments. Natural explanations. And those explanations are almost certainly correct. But the Silurian hypothesis pushes us to ask a harder question. How would we actually tell the difference between a natural release of carbon and one caused by industrial activity? The answer is not obvious at all. The chemical fingerprint of industrial activity in the geological record might look strikingly similar to certain natural events. Rapid carbon injection, temperature spikes, changes in ocean chemistry. These are the signatures we ourselves are leaving right now. And if we were to discover them in the distant past, our default assumption would almost certainly be that they came from natural causes. This is not an argument that a previous civilization actually existed. Let that be clear from the very beginning. Frank and Schmidt themselves emphasize that they strongly doubt any such civilization ever walked this earth. Their paper is a thought experiment, not a claim about reality. But what it does is reveal something important about the nature of scientific inquiry itself. It exposes the boundaries of what we can actually know and the assumptions we make without even realizing we are making them. We assume we are alone because no contrary evidence has been produced. But the Silurian hypothesis shows us that evidence of a previous industrial civilization might become effectively undetectable after only a few million years of geological action. In such a case, the absence of evidence tells us very little indeed. Of course, there are arguments pushing back against the possibility of previous civilizations. Strong arguments. If such a civilization had existed and exploited the planet's resources the way we have, we would expect to find signs of that exploitation. We would expect depleted mineral deposits, exhausted fossil fuel reserves, altered patterns in the fossil record itself. The fact that accessible coal and oil deposits were still sitting there waiting for us to discover suggests strongly that no one extracted them before. But even this argument carries caveats. A civilization that developed different technologies, one that never burned fossil fuels, one that left different kinds of traces than we do, could conceivably be invisible to us. And a civilization that predated the Carboniferous period, that existed before the great forests that eventually became our coal, would have had an entirely different resource base to work with. The further you dig into this question, the more it reveals about the limits of our knowledge. We view the past through a distorted lens, a lens smudged by time and geology and the bias of our own expectations. We find what we go looking for, and we rarely look for the things we do not expect to find. This is why the myths matter. Across cultures separated by entire oceans and thousands of years of history, humans have told stories of lost civilizations. Atlantis, Lemuria, Mu, the land of the gods before the flood. These stories are not proof, they are not evidence in any scientific sense, but they are fascinating because they are so persistent. Why do so many cultures remember a time before time itself, a golden age that ended in catastrophe? Maybe they are simply fantasies, projections of human longing onto an imagined past. Maybe they are distorted echoes of real but ordinary events, floods and earthquakes and the collapse of Bronze Age cities. Maybe they are nothing more than the human habit of imagining that things were once better than they are now. Or perhaps, buried somewhere in the collective memory of our species, there is a fragment of something we have forgotten, a shadow of knowledge lost to time. We will explore these myths in the chapters ahead. We will try to separate fact from fiction as far as we are able. We will look at what archaeology and geology actually tell us about the deep past, and we will confront the limits of what we can ever truly know. But for now, let this question settle into your mind. 4.5 billion years. 400 million years of complex life. 150 million years of dinosaurs. 300 years of industry. We assume we are the first. We assume we are alone. But the beach keeps stretching back into the darkness, and the sand keeps falling endlessly through our fingers. Chapter 2. The Silurian Hypothesis and the Puzzle of Deep Time. In 2018, a paper appeared in the International Journal of Astrobiology with an unusual premise. Two scientists, one an astrophysicist and one a climate scientist, had decided to take seriously a question that most researchers would have dismissed out of hand as ridiculous. Would it actually be possible to detect an industrial civilization in the geological record? The paper took its name from a fictional species featured in Doctor Who, but its implications were anything but fictional. Adam Frank of the University of Rochester and Gavin Schmidt of NASA approached the question with the rigor of serious scientific investigation. They were not claiming that a previous civilization had existed. They were asking whether we would know if it had. And the answer they reached was profoundly unsettling. The problem starts with time itself. Not human time, not historical time, geological time, the kind of time that makes our entire existence as a species look like a footnote, an afterthought. A rounding error in the vast ledger of Earth's history. Complex life first appeared on this planet roughly 540 million years ago during an event known as the Cambrian explosion. Before that moment, for billions of years, only simple single-celled organisms had existed. But once complex life took hold, it diversified with astonishing velocity. Fish appeared, plants colonized the land, insects evolved, amphibians crawled from the water, reptiles rose to dominance. The dinosaurs reigned for 150 million years. 150 million. Try to wrap your mind around that number. If you counted a single digit every second without pausing, it would take you almost 5 years just to reach 150 million. The age of dinosaurs endured for so long that a Tyrannosaurus rex lived closer in time to us than it did to a Stegosaurus. The late Cretaceous is separated from the late Jurassic by a greater expanse of time than the one that separates us from the extinction that wiped out the dinosaurs entirely. Within that vast stretch lived countless species we know absolutely nothing about. The fossil record is not a complete archive, it is a sampling, a fragmentary glimpse of what once existed. The conditions required for fossilization are rare and specific. An organism has to die in the right environment, be buried quickly, escape scavengers, and undergo the exact chemical processes that replace organic material with mineral. Most creatures that die simply rot and vanish without leaving the faintest trace. Scientists estimate that we have fossil evidence of perhaps 1% of all species that have ever existed. Some estimates place it considerably lower. The overwhelming majority of life that has lived on this planet left no record of any kind. They lived, they died, they disappeared. Now, apply this same logic to civilization. If a species had developed intelligence and technology 50 million years ago, 100 million years ago, or 200 million years ago, what traces would be left today? Frank and Schmidt examined this question systematically. They identified the kinds of signatures a technological civilization might leave in the geological record. Chemical anomalies in sediment, isotope ratios suggesting rapid carbon release, concentrations of synthetic materials, radioactive fallout from nuclear activity, shifts in biodiversity patterns. Then they asked how long these signatures might actually persist. The answer varies depending on the type of signature. Some markers of our own civilization will endure for millions of years. Radioactive isotopes from nuclear weapons testing have already spread across the entire planet and will remain detectable in sediment layers for enormous spans of time. Plutonium-239 has a half-life of 24,000 years, and its decay products will leave a permanent imprint. But other signatures are far more ephemeral. Plastics, which feel so permanent to us, will break down over thousands of years. They may leave behind chemical traces, but those traces will become increasingly difficult to distinguish from naturally occurring compounds over time. Concrete will erode. Metals will oxidize and scatter. Glass will shatter and eventually dissolve. The built environment, the cities and roads and structures that define our civilization, will simply cease to exist in any recognizable form. Erosion will grind them into nothing. Sediment will bury them. Tectonic forces will fold and crush them into unrecognizable shapes. After 1 million years, essentially nothing identifiable would remain above the surface. But the deeper signatures, the chemical fingerprints preserved in marine sediment and ice cores, might last much longer. And this is where Frank and Schmidt focused their attention. They observed that our own industrial civilization is currently leaving exactly the kinds of traces that might remain detectable across deep time. We are releasing enormous quantities of carbon dioxide into the atmosphere, altering the carbon isotope ratios in ways that will be preserved in sediment. We are spreading synthetic chemicals across the entire globe. We are driving a mass extinction event that will register in the fossil record as a sudden collapse of biodiversity. If a future civilization or a future intelligent species were to examine the geological record millions of years from now, they would see our impact. They would detect the carbon spike. They would register the extinction event. They would find chemical anomalies that would demand an explanation. But would they recognize it as the product of an industrial civilization? This is where the thought experiment becomes genuinely interesting. Frank and Schmidt examined past events in Earth's history that share certain characteristics with the impact we are having today. Events marked by rapid carbon release, global warming, ocean acidification, and mass extinction. The most striking example is the Paleocene-Eocene thermal maximum, an event that unfolded roughly 56 million years ago. Over a geologically brief interval, perhaps 10 to 20,000 years, enormous quantities of carbon entered the atmosphere. Global temperatures climbed by 5 to 8 degrees Celsius. Sea surface temperatures near the poles reached 23 degrees, comparable to what we see in modern subtropical waters today. The deep oceans lost their oxygen. Many species of marine organisms went extinct. The cause of this event is still debated. The leading hypothesis involves volcanic activity connected to the opening of the North Atlantic, specifically the massive eruptions that created what we now call the North Atlantic Igneous Province. Another possibility is the release of methane hydrates from the ocean floor, triggered by warming from volcanic carbon dioxide. Both explanations are natural, and both are probably correct. But Frank and Schmidt point to something crucial. The signatures of the PETM look remarkably similar to what we would expect from a technological civilization: rapid carbon injection, rising temperatures, ocean acidification, loss of biodiversity. If we assume that every such event must have a natural cause, we could conceivably miss evidence of something entirely different. Again, this is not a claim that the PETM was caused by a previous civilization. There is no evidence whatsoever to support such a claim, and the natural explanations are persuasive. The point is more subtle than that. The point is that our methods for studying the deep past were not designed to detect civilizations. We look for natural causes because we assume natural causes. And that assumption shapes what we find. The Silurian Hypothesis asks us to question that assumption, not to discard it, not to embrace wild speculation, but to recognize its presence and consider what it might be hiding. One of the strongest arguments against a previous industrial civilization is the presence of easily accessible resources. We found coal and oil near the surface, deposits that had accumulated over hundreds of millions of years. If a previous civilization had exploited these reserves, we would expect to find them depleted. The fact that they were patiently waiting for us suggests that no one extracted them before. It is a good argument, but it has limits. A civilization that arose before the Carboniferous period, before the great forests that eventually became coal even existed, would have had no fossil fuels to exploit. Such a civilization would have developed entirely different energy technologies. And even a civilization that existed after the Carboniferous might have followed different technological paths. Consider the diversity of human cultures throughout our own short history. Some societies developed metallurgy, others did not. Some built enormous cities, others remained nomadic. Technology is not deterministic. Different circumstances lead to different outcomes. A previous civilization could have left traces we simply do not recognize because we are searching for the wrong things. There is also the question of duration. Our industrial civilization is roughly 300 years old. If we were to destroy ourselves tomorrow through nuclear war or ecological collapse, our window of industrial activity would have been extraordinarily brief. A future geologist examining the sediment layer from our era would see a spike of carbon, chemicals, and radioactive isotopes lasting perhaps a few hundred years. After millions of years, that spike would be compressed into a layer perhaps a few centimeters thick, easy to overlook, easy to misinterpret. A previous civilization lasting a comparable length of time would leave an equally thin trace. And the further back in time you go, the harder it becomes to resolve such thin layers. The geological record grows increasingly compressed and distorted with age. Frank and Schmidt concluded their paper with a note of epistemic humility. They strongly doubt that any previous industrial civilization existed before our own. The balance of evidence suggests we are alone in Earth's history. But asking the question formally reveals useful insights about the nature of our knowledge and its limits. It shows us that we cannot be certain. The geological record is incomplete. Our methods have blind spots. The absence of evidence is not proof of absence, particularly when the evidence we seek might be inherently difficult to detect. It also reveals something important about the future. If we wish to leave a lasting mark on Earth's history, a mark that might still be detected millions of years from now, we are already doing it. The radioactive fallout from nuclear testing will persist for ages. The carbon we are releasing will alter isotope ratios in sediment around the world. The mass extinction we are causing will appear as a clear boundary in the fossil record, a moment when diversity collapsed and was replaced by something new. We are writing ourselves into the rock. Future geologists, whether human or otherwise, will find us there. But will they understand what they have found? Will they recognize the signature of a technological civilization? Or will they, like us, assume that all ancient events must have natural causes? The Silurian Hypothesis does not answer these questions, it merely raises them. And in raising them, it reminds us that the past is not as knowable as we sometimes assume. The Earth has had 4.5 billion years to accumulate secrets. Most of them are lost forever, buried beneath layers of time too thick to penetrate. We stand on the surface and gaze down into the abyss of deep time. We see fragments and shadows. We reconstruct what we can from incomplete evidence, and we tell ourselves stories about what once was. But the stories we tell are shaped by the questions we ask. If we never ask whether civilizations came before us, we will never design the methods needed to detect them. We will simply assume we are alone. And perhaps we are. But the Silurian Hypothesis reminds us that this assumption is precisely that, an assumption. The Earth keeps its secrets well, and the further back we look, the darker it becomes. Chapter 3. What would a civilization actually leave behind? Let us conduct a thought experiment of our own. Imagine that tomorrow every human being vanishes from the face of the Earth. No war, no plague, no apocalypse of any kind. We simply cease to exist. What would happen to everything we have built? This is not science fiction. This is forensic geology. This is asking what traces would persist and for how long. Because understanding what we would leave behind is the key to understanding what we might discover from the past. The first few years would see rapid decay. Power plants would shut down without maintenance. Within days, nuclear reactors would begin to overheat and fail. Fires would break out in cities around the world, sparked by lightning strikes or chemical reactions in abandoned factories. Without firefighters, these blazes would burn until they ran out of fuel. Within months, vegetation would begin reclaiming urban spaces. Grass would push its way through cracks in pavement. Vines would climb walls. Trees would sprout from gutters and from rooftops. The concrete jungle would become a real jungle, slowly, inexorably. Within decades, most wooden structures would collapse. Termites, rot, and weather would reduce houses and buildings to rubble. Steel structures would last longer, but not indefinitely. Without maintenance, rust would weaken supports. Bridges would fail. Skyscrapers would buckle and fall. Within a few centuries, almost all above-ground structures would be gone. The exceptions would be stone buildings in dry climates, places like the pyramids of Egypt or the ruins of Petra. But even these would eventually surrender. Sandstorms would wear away carvings. Earthquakes would topple walls. Given enough time, nothing on the surface would remain. But the deeper question is not what happens in centuries. It is what happens across millions of years. What would a geologist find if they examined the sediment layer from our era 100 million years from now? The first thing they would notice is the carbon. We have released roughly 550 billion tons of carbon into the atmosphere since the Industrial Revolution began. This carbon carries a distinctive isotopic signature. Fossil fuels, formed from ancient organic matter, contain less carbon-13 than the atmosphere does. When we burn them, we shift the ratio of carbon isotopes in the atmosphere, the ocean, and eventually the sediment itself. This shift is already detectable. Scientists studying ice cores and marine sediment can see the change beginning around 1750 and accelerating dramatically through the 20th century. This signal will persist for millions of years. Any future geologist examining sediment from our era will see the isotope anomaly and know that something unusual happened. The second thing they would notice is the mass extinction. We are currently in the midst of what many scientists call the sixth mass extinction. Species are disappearing at rates 100 to 1,000 times higher than the natural background rate. The fossil record will show a sudden collapse of biodiversity followed by the expansion of a handful of generalist species. This is exactly what we see at other extinction boundaries throughout the geological record. The end of the Cretaceous shows a sudden disappearance of dinosaurs and many other groups, followed by the rapid diversification of mammals and birds. The end of the Permian shows an even more dramatic collapse, with 90% of marine species and 70% of land species vanishing. Our own impact will appear as yet another such boundary. But there is something else that our era will leave behind. Something genuinely unprecedented in Earth's history: synthetic materials. Plastics are perhaps the most distinctive marker of human civilization. We produce roughly 400 million tons of plastic every single year. Much of it ends up in the environment, in landfills, in the ocean, scattered across every corner of the globe. Microplastics have been found in the deepest ocean trenches and on the highest mountain peaks. They are in the bodies of marine animals, in the soil, in the air we breathe. Plastic does not biodegrade within any meaningful time frame. It breaks down into smaller and smaller pieces, but the polymers themselves persist. Over millions of years, some of this plastic will become incorporated into sedimentary rock. It will form a distinctive layer, a stratum of synthetic polymers that has no natural equivalent. Scientists have already coined a term for such artifacts: technofossils. These are human-made materials that will persist in the geological record and potentially be detected by future observers. Plastic is the most obvious example, but there are others. Aluminum is exceptionally rare in pure form in nature. Before humans learned to extract it from bauxite ore, pure aluminum essentially did not exist on Earth's surface. Now we produce roughly 65 million tons per year. Aluminum artifacts that become buried in sediment will mark our era as distinctively as any fossil. Concrete is another candidate. We have produced so much concrete that it now rivals the total mass of all living plants on Earth. Concrete structures that sink into subsiding coastal areas or become buried in sediment will leave traces for millions of years. And then there is the radioactive signature. Between 1945 and 1963, above-ground nuclear weapons testing released radioactive isotopes into the atmosphere. These isotopes spread across the entire globe and settled into sediment everywhere. Plutonium, cesium, and other radionuclides created a global marker that will persist for tens of thousands of years. This radioactive layer is one of the proposed boundaries for the Anthropocene, the geological epoch defined by human impact on the planet. Scientists have identified sediment cores from around the world that show a sharp increase in radionuclides beginning in the 1950s. This signal is unmistakable and unprecedented. But here is the crucial question. If we found such signals in the deep past, would we even recognize them for what they are? Consider the radionuclide signature. Radioactive isotopes can be produced by natural processes. Cosmic rays striking the atmosphere generate certain radionuclides. Volcanic activity can release naturally occurring radioactive materials. Uranium deposits undergo spontaneous fission. In fact, scientists have found natural nuclear reactors. About 2 billion years ago, in what is now Gabon in Africa, geological conditions created several nuclear fission reactors at a site called Oklo. Uranium concentrated in certain rock formations reached critical mass and sustained nuclear reactions for hundreds of thousands of years. These natural reactors left a distinctive isotopic signature that scientists can still detect today. The Oklo reactors are fascinating because they show us what a natural nuclear event actually looks like. They provide a baseline for comparison. The isotope ratios at Oklo differ from those produced by human nuclear weapons. A future geologist familiar with natural nuclear processes might be able to distinguish between a natural reactor and an artificial one. But without that knowledge, without familiarity with human nuclear technology, they might simply classify both as unusual natural phenomena. The same logic applies to other signatures. A carbon isotope anomaly could be caused by volcanic activity, methane release, or an industrial civilization burning fossil fuels. An extinction event could be triggered by an asteroid impact, climate change, or the activities of a dominant species that disrupted ecosystems. A layer of unusual materials could be explained by geological processes we do not fully understand. Science works by looking for natural explanations first. This is appropriate and necessary. Most phenomena do have natural causes, and invoking exotic explanations without strong evidence leads to error. But this methodological principle also creates a blind spot. If something unusual were caused by a technological civilization, we might not recognize it because we are not looking for that explanation. Frank and Schmidt make an interesting observation about this. They note that we already have extensive archives of geological data collected for other purposes. Ice cores drilled to study climate. Sediment cores extracted to investigate ocean chemistry. Rock samples analyzed for mineral content. These archives could potentially contain evidence of past civilizations that were never recognized because no one was looking for them. The evidence might already be sitting in boxes in university basements, cataloged for entirely different purposes, misidentified as natural anomalies. We would never know unless we specifically searched. This is not a call to re-examine every sediment core for evidence of ancient aliens. It is a call to humility about the limits of our knowledge. We see what we look for. We interpret what we see within frameworks shaped by our expectations. If the frameworks are incomplete, our interpretations will be incomplete too. The Deep Past is not a book we can read freely. It is a palimpsest, a manuscript written over and over again with each successive layer partially obscuring what came before. We can read the most recent layers with reasonable confidence. But the older the writing, the harder it becomes to decipher. And the oldest writings of all, whatever they may have said, are lost beneath layer upon layer of subsequent geology. Chapter 4. The Earth as an Eraser. To understand why the Deep Past is so difficult to read, we need to understand the Earth itself. We tend to think of our planet as a stable platform, a reliable backdrop against which the drama of life plays out. But the Earth is not stable. It is a dynamic, evolving, restless system. And that restlessness comes at a cost. The processes that make this planet habitable, that drive the weather, create soil, and move nutrients around the globe, are the very same processes that destroy evidence of the past. Consider erosion. Every moment, rain is falling somewhere in the world. That water runs across the land, picking up tiny particles of rock, dissolving minerals, carrying sediment toward lower ground. Rivers carry that sediment to the sea. Wind adds its own contribution, blasting exposed rock with particles of sand and grinding away the surface. Freezing water expands in cracks, shattering boulders into pebbles, pebbles into grains. Over thousands of years, these seemingly gentle processes can wear down entire mountain ranges. Over millions of years, they can reduce continents to rubble, given enough time. Now imagine a city built on an exposed surface. Stone buildings, concrete towers, steel frameworks. They seem permanent to us, but to geology, they are fleeting. Frost would crack the stone, acid rain would dissolve the concrete. Wind and water would carry away the fragments. Given 10,000 years, little would remain above ground. Given 1,000,000 years, nothing would be recognizable. But erosion is only one mechanism of destruction. Consider plate tectonics. The Earth's surface is divided into roughly 15 major plates and dozens of smaller ones. These plates float on a layer of partially molten rock called the asthenosphere. They move slowly, just a few centimeters per year, but over millions of years those centimeters add up to thousands of kilometers. Where plates collide, one often slides beneath the other in a process called subduction. The subducting plate descends into the mantle, carrying with it everything on its surface. Sediment, rock, fossils, artifacts. All of it melts into the magma and becomes part of the Earth's interior. This material may eventually resurface through volcanic activity, but any structure or organization it once had is utterly destroyed. The Pacific Plate, the largest tectonic plate on Earth, is almost entirely oceanic crust. It is being subducted beneath the surrounding plates along most of its boundaries. Any artifacts deposited on the Pacific seafloor will eventually be pulled into the mantle and destroyed. Given enough time, the entire current ocean floor will be recycled. Scientists estimate that no oceanic crust older than about 200 million years exists today. Everything older has been subducted. This means that any evidence of activity that occurred on the ocean floor before that time is simply gone. It has been melted, mixed, and reincorporated into the planet's interior. Continental crust is more durable. It is less dense than oceanic crust and tends to float on top rather than subducting. The oldest known continental crust is about 4 billion years old, found in places like the Canadian Shield and the Pilbara region of Australia. But even continental crust is not permanent. Continents collide and mountains rise. The Himalayas are still growing as India pushes into Asia. The Alps formed from the collision of Africa and Europe. When mountains rise, they also erode. Material from the peaks is carried down by rivers and deposited in basins and ocean floors. Over tens of millions of years, entire mountain ranges can be worn down to their roots. The rock beneath your feet has a history. It may have been part of a mountain chain 300 million years ago, eroded to a plain, buried under sediment, compressed into new rock, uplifted by another collision, and exposed again at the surface. The geological cycle operates continuously, transforming and destroying. Now add metamorphism to the picture. When rock is buried deeply enough or subjected to enough heat and pressure, it changes. The minerals within it recrystallize. The structures it contains are deformed. Fossils become stretched and distorted. Sedimentary layers become schists and gneisses, their original characteristics obscured. The oldest rocks on Earth have been so thoroughly metamorphosed that reading their history is extraordinarily difficult. Scientists use sophisticated techniques to extract information from zircon crystals and other resistant minerals, but the picture they reconstruct is fragmentary at best. The deep past is not merely distant, it is transformed. Consider the implications for detecting a previous civilization. Any artifacts on the surface would be eroded away within tens of thousands of years. Any artifacts on the ocean floor would be subducted within hundreds of millions of years. Any artifacts deeply buried would be metamorphosed beyond recognition. The only traces that might survive would be chemical signatures embedded in sedimentary rock that formed in stable environments and avoided both subduction and deep burial. Marine sediment deposited on continental shelves. Lakebed deposits in tectonically quiet regions. Materials that became incorporated into rock that has remained near the surface. Even these survivors face significant challenges. Chemical signatures can be altered by fluid flow through rock. Isotope ratios can be reset by heating events. Biological activity can modify the chemistry of sediments long after they were deposited. The geological record is not a pristine archive. It is a palimpsest written over and over, with earlier texts becoming increasingly illegible. The fossil record illustrates this beautifully. Paleontologists estimate that we have discovered fossils from perhaps 1% of all species that ever lived. Some estimates put it even lower. The vast majority of organisms that existed left no trace whatsoever. They lived and died in environments where fossilization did not occur. Their remains decayed. Their bones dissolved. Their shells were crushed. Nothing remains. For an organism to become a fossil, it must die in the right place at the right time. It must be buried quickly before scavengers and decomposers destroy it. It must be in an environment where minerals can replace organic tissue. The sediment must remain undisturbed long enough for lithification to occur. The rock must survive subsequent erosion, subduction, and metamorphism. And finally, the fossil must be exposed at the surface where a paleontologist can find it. Each of these steps is improbable. The cumulative probability is vanishingly small. The fossil record is not a comprehensive archive of past life. It is a series of lucky accidents, windows into the past opened by chance alone. Now apply this logic to civilization. A city is larger than a dinosaur, but it is not more durable. Stone and metal resist decay longer than flesh and bone, but they are still subject to the same geological forces. A skyscraper buried in sediment will be compressed, fractured, and eventually transformed into something unrecognizable. The oldest human artifacts we have found date back roughly 3 million years. Stone tools from the early hominins, shaped cobbles and flakes, that represent the very dawn of technology. These artifacts survived because they were made of durable material and buried in suitable environments. But they are extraordinarily rare. For every tool we find, thousands were lost to erosion, destruction, or simple bad luck. Extend this backward in time. If a civilization had existed 50 million years ago, any stone tools they produced would have had 50 times longer to be destroyed. The probability of finding even one artifact would be vanishingly small. And this assumes they made stone tools at all. What if they developed different technologies? What if their artifacts were made of materials that do not survive geological time? What if they built in ways we cannot even imagine, leaving traces we would not recognize as artifacts even if we stumbled directly upon them? The Earth has had 4.5 billion years to accumulate evidence of everything that has ever happened on its surface. And it has had 4.5 billion years to destroy that evidence. The net result is a fragmentary record, a handful of snapshots from a film billions of frames long. Most of what has occurred on this planet is simply gone, erased by the very processes that make the planet dynamic and alive. This is not a defect of the geological record. It is the nature of planets. The same processes that create habitable environments also destroy the traces of what came before. Erosion shapes landscapes and provides nutrients for life. Plate tectonics recycles crust and generates volcanic activity that releases gases into the atmosphere. Metamorphism creates new minerals and concentrates valuable resources. A dead planet, geologically inert, might preserve evidence better. Mars has no plate tectonics. Its surface features can survive for billions of years. The Moon has even less erosion and even better preservation. But dead planets are not good places for life. The very processes that make Earth habitable also make it a graveyard for evidence. There is a profound irony here. If intelligent life evolved elsewhere in the solar system and left artifacts on Mars or the Moon, we might actually find them. Those artifacts would be preserved almost indefinitely in the airless, tectonically dead environments of those worlds. But if intelligent life evolved on Earth and was destroyed, its traces would be erased by the planet's own vitality. We are trapped in a dynamic system, surrounded by evidence of current life and recent history, but largely blind to what came before. The geological record is a keyhole through which we glimpse fragments of the past. And the further back we look, the narrower the keyhole becomes. The oldest recognizable structures in the rock record are stromatolites, layered formations created by microbial mats. These date back over 3 billion years, but they are simple structures, the accumulated product of countless generations of microbes. They persist because they are made of durable minerals and formed in environments favorable to preservation. Complex structures are far harder to preserve. Delicate organisms, intricate artifacts, anything with fine detail is easily destroyed. The geological record strongly favors the simple, durable, and widespread over the complex, fragile, and localized. A civilization is, by definition, localized. It occupies specific regions. Its artifacts are concentrated in cities and settlements. Even if individual objects are durable, their distribution is limited. Compare this to a widespread organism like cyanobacteria, which colonized oceans around the world and left traces in rock formations across every continent. The signature of a civilization is inherently more fragile than the signature of widespread biological activity. This is another reason why detecting a previous industrial civilization would be so difficult. Even if they existed, even if they left traces, those traces would be concentrated in small areas that might easily have been destroyed. The Earth is a beautiful planet. It supports an astonishing diversity of life. Its dynamic geology creates mountains and valleys, rivers and oceans, climates and ecosystems beyond counting. But this dynamism comes at a cost. The Earth forgets. It buries and transforms and recycles. It grinds down mountains and subducts ocean floors. It metamorphoses rock and resets isotope ratios. Given enough time, it erases almost everything. If we want to understand the deep past, we must work with fragments. We must accept uncertainty. We must recognize that the absence of evidence often reflects the absence of preservation rather than the absence of existence. The Earth is not a museum, it is an eraser. And it has been working for 4.5 billion years. Chapter 5. The Paleocene-Eocene thermal maximum and the ancient carbon spikes. 56 million years ago, something extraordinary happened. The Earth, already warm by modern standards, suddenly became much warmer. Over a period of perhaps 20,000 years, global temperatures climbed by 5 to 8 degrees. The Arctic Ocean reached temperatures of 23 degrees Celsius. Tropical seas became so hot that they approached the limits of what marine life could tolerate. The deep oceans lost their oxygen. Species went extinct. And then, slowly, over the course of about 200,000 years, the planet recovered. This event is called the Paleocene-Eocene thermal maximum, or PETM. It marks the boundary between two geological epochs, and it is one of the most intensively studied events in deep Earth history. Scientists have drilled sediment cores from ocean floors around the world, extracted cores from ancient ice deposits, and analyzed the chemistry of shells and rocks from this period. The picture that emerges is both fascinating and troubling. The PETM was caused by a massive release of carbon into the atmosphere. Scientists estimate that between 2,000 and 5,000 billion tons of carbon entered the system over a geologically short period. This carbon had a distinctive isotopic signature. It was depleted in carbon-13, indicating that it came from an organic source rather than from volcanic emissions. The leading hypothesis is that the carbon came from methane hydrates. These are ice-like deposits of methane trapped in sediment on continental margins and beneath permafrost. When ocean temperatures rise, these hydrates become unstable and release their methane into the water and atmosphere. Methane is a potent greenhouse gas, and its release would cause further warming, which would release more methane, creating a feedback loop. But what triggered the initial warming that destabilized the hydrates? This is where theories diverge. Some scientists point to volcanic activity. The North Atlantic igneous province was forming at this time as Greenland separated from Europe. Massive volcanic eruptions released carbon dioxide into the atmosphere, which caused initial warming, which then triggered the methane release. Other researchers suggest that changes in Earth's orbit played a role. The planet's orbital parameters vary on cycles of tens to hundreds of thousands of years, affecting how much solar radiation reaches different parts of the surface. A particular configuration might have pushed temperatures over a threshold, initiating the cascade. Whatever the trigger, the consequences were dramatic. The fossil record shows rapid changes in flora and fauna. In North America, the subtropical species that had dominated the previous epoch gave way to more tropical forms. The ancestors of modern horses appeared, smaller than their predecessors, an adaptation to the warmer climate. In the oceans, many species of foraminifera, the tiny shelled organisms that form the basis of marine food webs, went extinct. The PETM is important because it is the closest natural analog to what we are doing today. We are releasing carbon into the atmosphere at a rate that rivals or exceeds the PETM. Our carbon also has a depleted carbon-13 signature because we are burning fossil fuels that formed from ancient organic matter. The climate system is responding with rising temperatures, ocean acidification, and changing ecosystems. But the PETM is also important for another reason. It is exactly the kind of event that the Silurian Hypothesis asks us to consider: a rapid carbon release, a global warming event, changes in ocean chemistry, mass extinctions. These are the signatures that an industrial civilization might leave. And while the natural explanations for the PETM are compelling, the thought experiment asks whether we would even recognize an artificial cause if one existed. Let us be absolutely clear. There is no evidence that the PETM was caused by anything other than natural processes. The volcanic hypothesis has strong support. The methane hydrate mechanism is well understood. No synthetic materials or artificial compounds have been found in PETM sediments. Scientists who study this event do not believe it was caused by a previous civilization, and there is no reason to think otherwise. But the Silurian hypothesis is not about proving that such a civilization existed. It is about understanding the limits of our detection capabilities. And the PETM provides a useful test case. Consider what we would look for if we wanted to distinguish between a natural carbon release and an artificial one. Both would leave a carbon isotope excursion. Both would cause warming and ocean acidification. Both would drive extinctions. The differences would be subtle. A natural release would probably show gradual onset, with carbon being added over thousands of years. An industrial release might be more abrupt, occurring over centuries rather than millennia. A natural release would involve mostly carbon dioxide. An industrial release might include other chemicals, specific synthetic compounds, traces of heavy metals from mining and manufacturing. A natural release would not produce radioactive isotopes. A civilization that used nuclear technology would leave radionuclides in the sediment, even if only from a brief period of activity. These differences are detectable in principle, but they require specifically looking for them. Standard geological investigations of events like the PETM focus on establishing the timing and magnitude of the carbon release, identifying the carbon source, and understanding the climatic consequences. They do not typically look for artificial compounds or radioactive anomalies. These would be dismissed as contamination or attributed to natural processes. So let us imagine a hypothetical. Suppose that the PETM was not purely natural. Suppose that 56 million years ago, a technological civilization existed on Earth. They were burning fossil fuels, manufacturing chemicals, perhaps even operating nuclear reactors. Over a few centuries, they released enough carbon and produced enough environmental disruption to trigger the cascading effects we see in the geological record. Then they collapsed. The warming they caused continued for thousands of years, as methane hydrates destabilized and released more carbon. The extinction event spread through ecosystems. Eventually, the planet recovered, but the original civilization was gone. What traces would remain 56 million years later? The carbon isotope excursion would still be visible. The extinction boundary would be clear, but the radioactive isotopes would have decayed to undetectability. The synthetic chemicals would have broken down. The physical artifacts would be long gone, subducted, eroded, metamorphosed beyond recognition. We would see the PETM and attribute it to volcanoes or methane hydrates. We would not have the specific evidence needed to identify an industrial cause, even though the artificial event might have left the same basic pattern. Again, this is speculation. There is no indication that the PETM was anything other than natural, but the scenario is not impossible, and it illustrates the fundamental problem with distant past events. They look similar whether their causes are natural or artificial. Without very specific evidence, we cannot tell the difference. The PETM is not the only such event in Earth's history. There are other ancient carbon spikes, other warming events, other mass extinctions. The Permian-Triassic extinction at the boundary of these two periods was the largest extinction event in Earth's history. 90% of marine species and 70% of land species went extinct. The cause was massive volcanic activity in what is now Siberia, combined with other factors. The Cretaceous-Paleogene extinction that killed the dinosaurs was triggered by an asteroid impact, combined with volcanic activity in India. The Toarcian oceanic anoxic event 75 million years ago showed rapid warming and ocean deoxygenation. The list goes on. Each of these events involved environmental disruption on a scale that might be compared to our own current impact. Each represents exactly the kind of catastrophic discontinuity that might be caused by civilizations, an industrial species that destabilized its climate, a spacefaring civilization that faced an existential threat. The natural explanations are almost certainly correct, but the question of how we would recognize an artificial cause remains open. The deeper lesson of the PETM and similar events is about the nature of scientific inquiry itself. We build models based on what we know. We look for patterns we expect to find. We are very good at explaining phenomena within our existing frameworks, but we are less good at detecting phenomena that fall outside those frameworks. If a previous civilization existed and left traces in the geological record, those traces would likely be interpreted as natural events. A carbon spike would be attributed to volcanoes or methane. A mass extinction would be blamed on climate change or asteroid impact. Unusual chemical signatures would be explained by unknown geological processes. This is not a flaw in science. This is the conservative methodology that prevents us from inventing explanations when simpler ones suffice. Extraordinary claims require extraordinary evidence, and no extraordinary evidence for previous civilizations has been found. But the Silurian hypothesis reminds us that ordinary evidence might be invisible to investigations not designed to find it. The absence of extraordinary evidence does not mean that nothing unusual occurred. It might simply mean that the unusual became ordinary over geological time. The PETM ended about 200,000 years after it began. The climate cooled, the oceans recovered. New species evolved to fill the ecological niches left vacant by extinction. Life went on. Whatever caused the PETM, natural or otherwise, it passed into history. The Earth healed. The evidence was buried under millions of years of sediment, and we, 56 million years later, piece together fragments and debate interpretations. The Earth keeps its secrets, and time is very, very long. Chapter 6. The Myths That Refuse to Die. Every culture has a story about the time before, a golden age when gods walked among men, a paradise lost to catastrophe, a civilization that reached heights we can barely imagine before being swept away by flood or fire or the wrath of heaven. These stories span continents and millennia. They appear in cultures that had no contact with each other, separated by oceans and centuries. And they refuse to go away. Atlantis is the most famous. The story comes from Plato, the Greek philosopher who lived in the 4th century before the Common Era. In 2 of his dialogues, the Timaeus and the Critias, Plato describes an island empire that existed 9,000 years before his own time. Atlantis was larger than Libya and Asia combined, he wrote. It possessed advanced technology, vast wealth, and a powerful military. Its people grew arrogant and decadent, and the gods destroyed them in a single day and night of earthquakes and floods. The island sank beneath the waves and was forgotten. Most scholars believe Plato invented Atlantis as a literary device. The story serves his philosophical purpose, illustrating the dangers of hubris and the impermanence of worldly power. There is no mention of Atlantis in any source before Plato. No Egyptian records describe such an empire, despite Plato's claim that the story came from Egyptian priests. No archaeological evidence supports the existence of a continent-sized island in the Atlantic. And yet, the story persists. For over 2,000 years, people have searched for Atlantis. Expeditions have explored the Mediterranean, the Caribbean, the coast of Spain, the depths of the Atlantic Ocean. Every few years, someone claims to have found it. Every claim falls apart under scrutiny. Why does this story have such power? Why do people want so badly to believe in a lost civilization that almost certainly never existed? Part of the answer is psychological. Humans are nostalgic creatures. We remember the past as better than it was. We imagine that previous generations had wisdom we have lost. The idea of a golden age appeals to something deep in our nature, a longing for a time when things were simpler, purer, more meaningful. Part of the answer is also epistemological. We know that history is incomplete. We know that civilizations have risen and fallen. We know that much of the past is lost to us forever. The idea that there might be more lost than we realize is not unreasonable. It is actually quite plausible. The question is how much and what kind. Atlantis is not the only lost continent in mythology. Lemuria was proposed in the 19th century by zoologists trying to explain the distribution of lemur fossils across Madagascar and India. They hypothesized a land bridge that had sunk beneath the Indian Ocean. When plate tectonics explained the fossil distribution through continental drift, the scientific basis for Lemuria vanished, but the name lived on in esoteric traditions, transformed into a lost civilization of advanced beings. Mu is another. James Churchward, a British writer of the early 20th century, claimed to have discovered ancient tablets in India that described a continent in the Pacific Ocean. According to Churchward, Mu was the original homeland of humanity, destroyed by volcanic cataclysm about 12,000 years ago. There is no evidence for any of this. The tablets Churchward described have never been produced. The geological evidence directly contradicts the existence of a sunken Pacific continent. The Pacific Ocean floor is entirely oceanic crust, created at mid-ocean ridges and moving slowly towards subduction zones at the edges. Continental crust, the kind that forms land masses, is absent. There is no mechanism by which a continent could sink in this region. The islands of the Pacific are volcanic peaks. not the remnants of drowned mountains. Yet Mu and Lemuria continue to feature in alternative history books and websites. People want to believe. The psychological need for lost golden ages overwhelms the geological evidence against them. But there is another category of lost civilization stories that deserves more careful attention. Stories that may be distorted memories of real events rather than pure fantasy. The flood myth is nearly universal. Cultures across the world tell stories of a great deluge that destroyed an earlier world. Noah's flood in the Hebrew tradition. Deucalion's flood in Greek mythology. Manu and the fish in Hindu scripture. Utnapishtim in the Gilgamesh epic. The Hopi emergence story. Chinese legends of Gun and Yu. Aboriginal Australian accounts of rising seas. These stories cannot all be copying each other. Many come from cultures that had no contact. The simplest explanation is that they reflect real experiences of flooding. And we know that such flooding occurred at the end of the last ice age, roughly 12,000 years ago. Global sea levels rose dramatically. Ice sheets that had covered much of North America and Europe melted. Water that had been locked in glaciers poured into the oceans. Sea levels rose by over 100 meters, flooding coastal plains that had been inhabited for thousands of years. This was not a single catastrophic flood, but a prolonged process lasting millennia. However, there were periods of rapid sea level rise, meltwater pulses, when glacial lakes burst through ice dams and released enormous volumes of water. These events could have caused regional flooding that seemed apocalyptic to those who experienced it. The Black Sea flood hypothesis suggests that around 5,600 years before the Common Era, rising Mediterranean waters breached the Bosporus and flooded the Black Sea basin, which had been a freshwater lake. The flooding would have been rapid by human standards, perhaps a few decades. Coastal settlements would have been destroyed. Survivors would have fled, carrying stories of the disaster. This hypothesis is debated. Some geologists support it. Others argue that the flooding was more gradual. But the broader point stands. Real flooding occurred at the end of the Ice Age. Coastal populations were displaced. Memories of these events could have been transmitted across generations and transformed into mythology. The same logic applies to other stories of lost lands. The submerged landscape of Doggerland, which once connected Britain to continental Europe, supported human populations for thousands of years before being inundated. Aboriginal Australian oral traditions describe coastal features that have been underwater for over 7,000 years. These are not myths of fictional places, but memories of real geography preserved in story form. This does not mean that Atlantis was real. Plato's description does not match any known submerged landscape. The scale he describes, a continent larger than Libya and Asia, is impossible, but it does mean that some lost land stories may have kernels of truth buried within them. The challenge is separating memory from invention, history from myth. Stories change in the telling. Details are added and subtracted. Ordinary events become extraordinary. A flooded valley becomes a drowned continent. A collapsed Bronze Age city becomes an empire that ruled the world. The human memory is not a reliable archive. It is a creative process that reconstructs the past based on present needs and beliefs. Oral traditions can preserve information across millennia, but they also transform it. The core of a story may be true, while the details are entirely fictional. This is why mythology cannot serve as evidence for lost civilizations. Stories of Atlantis and Mu and Lemuria are interesting cultural artifacts. They tell us about human psychology and the need for origin stories, but they do not tell us about the actual deep past of the planet. What they do tell us is that humans have always sensed that there is more to history than we remember, that civilizations rise and fall, that knowledge is lost, that the past contains secrets we may never fully recover. This intuition is correct. The past does contain secrets. The geological record is incomplete. The archaeological record barely scratches the surface. There is much we do not know and may never know about what occurred on this planet before written history began. But intuition is not evidence. And the secrets of the past, whatever they may be, cannot be accessed through mythology. They can only be approached through the careful, patient work of science. Through digging in the ground and drilling into sediment, through analyzing isotopes and dating artifacts. through building models and testing hypotheses. The myths that refuse to die tell us about ourselves. They tell us that we are creatures who need stories, who cannot accept that the past might be truly lost. They tell us that we will always imagine golden ages and lost paradises, because imagining them fulfills a deep psychological need. But the Earth does not care about our psychological needs. It keeps its secrets regardless of our wishes. And the only way to learn those secrets is to ask questions the right way, not through mythology, through science. Chapter 7. Göbekli Tepe and the Edge of Memory. In southeastern Turkey, about 15 kilometers from the city of Samlesfri, a hill rises from the dusty plain. The locals call it Göbekli Tepe, which means potbelly hill in Turkish. For thousands of years, farmers walked past it without giving it a second thought. It looked like a natural formation covered in grass and scrub, unremarkable in a landscape full of hills. In 1963, archaeologists from the University of Istanbul and the University of Chicago surveyed the area. They noticed some broken limestone on the surface and a few signs of human activity. They concluded the site was an abandoned medieval cemetery not worth excavating. They moved on. 30 years later, a German archaeologist named Klaus Schmidt visited the hill. He saw something the earlier team had missed. The broken stones were not random rubble, they were worked. They had been shaped by human hands. Schmidt began excavating in 1995. What he found changed our understanding of human history. Beneath the surface lay massive stone structures, circular enclosures ringed by T-shaped pillars, some standing over 5 meters tall and weighing up to 50 tons. The pillars were carved with intricate reliefs of animals: lions, bulls, foxes, snakes, scorpions, vultures. Human figures appeared too, stylized and mysterious. The workmanship was sophisticated. The scale was monumental. Carbon dating revealed the impossible truth. The oldest structures at Göbekli Tepe were built around 9,600 years before the Common Era. They are 11,600 years old. They predate Stonehenge by 6,000 years. They predate the Egyptian pyramids by 7,000 years. They are the oldest known monumental structures on Earth. And they were built by hunter-gatherers. This is what makes Göbekli Tepe revolutionary. The conventional story of human development held that civilization followed agriculture. First, humans learned to farm. Farming created food surpluses. Surpluses allowed some people to specialize in activities other than food production. Specialization led to social hierarchy, organized religion, and monumental architecture. This sequence seemed logical and was supported by archaeological evidence from the Near East and elsewhere. Göbekli Tepe inverts this sequence. The people who built it were not farmers. There is no evidence of domesticated plants or animals at the site. They were hunter-gatherers who relied on wild game and foraged plants. Yet they organized themselves to carve, transport, and erect massive stone pillars. They created elaborate symbolic art. They built structures that must have required hundreds of workers and years of coordinated labor. How is this possible? How did hunter-gatherers living in small mobile bands manage a construction project that rivals anything from later civilizations? The answer appears to be religion, or at least shared belief systems powerful enough to motivate extraordinary collective effort. Göbekli Tepe was not a settlement. There are no houses, no storage facilities, no signs of permanent habitation. It was a ritual center, a place of pilgrimage where people from across the region gathered for ceremonies and feasts. The animal bones found at the site support this interpretation. Thousands of animal remains, mostly gazelle and aurochs, show signs of butchering and cooking. The scale suggests large feasts, events that brought together far more people than any single band could provide. These gatherings would have required coordination, planning, and a shared sense of purpose. Schmidt proposed that Göbekli Tepe represented a fundamental shift in human consciousness. The desire to build permanent sacred structures, to create places where the gods could be worshipped, preceded and perhaps drove the development of agriculture. People settled near the site, not to farm but to participate in religious activities. Once settled, they began domesticating plants and animals to support their new sedentary lifestyle. This is speculation, but it is informed speculation based on evidence, and it forces us to reconsider what we think we know about the origins of civilization. If Schmidt is right, then our standard narrative of human development is incorrect. The rise of civilization was not driven primarily by economics but by ideology. Humans built society not to feed themselves but to worship their gods. The cities came later. But the deeper significance of Göbekli Tepe for our inquiry is what it reveals about our ignorance. For 11,000 years, these extraordinary structures lay beneath a hill in Turkey. Farmers plowed fields above them. Travelers walked past without a glance. Even professional archaeologists overlooked the site for decades. If Göbekli Tepe could hide in plain sight for so long, what else might be hidden? How many other sites of comparable importance remain undiscovered? The scale of Göbekli Tepe is staggering. The excavated portion represents only a small fraction of the site. Ground-penetrating radar surveys suggest that many more enclosures remain buried beneath the surface. Some estimates put the total size of the complex at over 20 acres. Schmidt believed the site might hold secrets that would take generations to fully reveal. And Göbekli Tepe is not unique. Related sites have been discovered throughout the region. Karahan Tepe, about 40 kilometers from Göbekli Tepe, contains similar pillars and enclosures dating to roughly the same period. Other sites are being investigated as archaeologists realize that a whole forgotten culture once thrived in this region. These people, whoever they were, represent a phase of human history that we are only beginning to understand. They lived at the dawn of what we call civilization, but they are not part of any civilization we had previously recognized. They are a ghost culture, a forgotten people whose monuments lay hidden for millennia. What else lies hidden? The question is both thrilling and humbling. Archaeology is a young science. Systematic excavation began only in the 19th century. Most of the world has never been thoroughly surveyed. Entire regions remain archaeologically unexplored. Even in well-studied areas, new discoveries are made regularly. The oldest known human artifacts are pushed further back in time every few years. The origins of agriculture, writing, metallurgy, and urban life are all being revised as new evidence emerges. What we know about the deep human past is a small fraction of what actually happened. The rest is lost to us, buried under earth and sediment, destroyed by time and circumstance. Some of it will never be recovered. Some will emerge only by accident, like Göbekli Tepe itself. And some may remain hidden forever beneath modern cities, or under the sea, or deep in unexplored regions of the world. This has implications for the Silurian hypothesis. If a civilization comparable to our own had existed even in recent geological times, say 1 million years ago, its traces could easily have escaped detection. The timescales are different from Göbekli Tepe. 1 million years is far longer than 11,000. But the principle is similar. Just because we have not found evidence does not mean evidence does not exist. It means we have not found it. And as Göbekli Tepe demonstrates, evidence can remain hidden, even when it exists, even when it is massive and elaborate, even when it lies beneath farmland visited by people for millennia. The site teaches humility. It teaches that our knowledge of the past is incomplete. It teaches that surprises await us beneath the surface. And it teaches that civilizations, or at least complex organized societies, can arise in unexpected contexts and leave unexpected traces. Göbekli Tepe is not evidence of a lost high civilization in the sense of Atlantis or Mu. The people who built it did not have metal tools or writing or industrial technology. They were hunter-gatherers who achieved something remarkable within the constraints of their world. Their achievement was social and spiritual, not technological. But the site expands our sense of what is possible. It shows that humans were capable of sophisticated organization and monumental construction far earlier than we thought. It suggests that the deep human past may be richer and more complex than our sparse evidence reveals. And it reminds us that memory has an edge. Beyond that edge, the past becomes silent. We can dig and analyze and reconstruct, but we cannot remember what our ancestors forgot. The stones of Göbekli Tepe stand witness to a world we barely understand. They survived because they were buried. They were found because an archaeologist looked more carefully than those who came before. They remain after 11,000 years to remind us that the past is not empty. It is merely forgotten. Chapter 8. The Younger Dryas Catastrophe. 12,800 years ago, The Earth was warming. The great ice sheets that had covered much of North America and Europe were retreating. Sea levels were rising. Forests were spreading north. Mammoths and mastodons roamed a landscape becoming greener by the century. The Ice Age was ending, and a new world was being born. Then something happened. Within a span of perhaps a single year, possibly less, temperatures in the northern hemisphere plunged. In Greenland, the temperature dropped by as much as 14 degrees Celsius almost overnight. The warming trend reversed. Ice sheets stabilized or began advancing again. The transition to the modern climate, which had seemed inevitable, was put on hold. This cold period lasted roughly 1,200 years. Scientists call it the Younger Dryas, named after a small Arctic flower called Dryas octopetala that flourished during this time in regions where it had not grown for millennia. The Younger Dryas was not a return to full glacial conditions, but it was a severe reversal, a last gasp of the Ice Age before the final warming. The Younger Dryas is one of the most studied and debated events in recent Earth history. Its cause remains controversial. The mainstream explanation involves changes in ocean circulation. As ice sheets melted, vast quantities of fresh water poured into the North Atlantic, potentially from the catastrophic drainage of glacial lakes. This fresh water was less dense than the salty seawater and floated on top, disrupting the thermohaline circulation that brings warm water from the tropics to northern Europe and North America. Without this oceanic heat pump, temperatures plunged. This explanation is well supported by evidence. The timing coincides with probable meltwater releases. Sediment cores show changes in ocean chemistry consistent with altered circulation. Climate models can reproduce the cooling when forced with massive freshwater input. Most scientists accept some version of this hypothesis. But there is another theory, one that is more controversial, more dramatic, and potentially more relevant to our question about previous civilizations. In 2007, a group of researchers proposed that the Younger Dryas was triggered by a cosmic impact. They suggested that a comet or asteroid, or perhaps multiple fragments of a disintegrating comet, struck Earth approximately 12,900 years ago. The impact, they argued, caused massive wildfires, darkened the skies with dust, destabilized ice sheets, and triggered the rapid cooling that followed. This is known as the Younger Dryas impact hypothesis. It has been vigorously debated, criticized, and defended in the years since it was proposed. The scientific community remains divided, with many researchers rejecting the hypothesis and others continuing to find supporting evidence. The proponents point to several lines of evidence. At sites across North America and in some locations in Europe, they have found a distinctive layer in the sediment corresponding to the onset of the Younger Dryas. This layer contains unusual materials, tiny spherules of glass and metal that appear to have formed at extremely high temperatures. Nanodiamonds, microscopic crystals that can form under the intense pressure of an impact. Elevated concentrations of platinum and iridium, elements common in asteroids but rare on Earth's surface. Shocked quartz, grains that show the distinctive fracture patterns caused by extreme pressure. Critics have challenged each of these findings. They have questioned the dating of the sediment layers. They have proposed alternative explanations for the spherules and nanodiamonds. They have pointed out inconsistencies in the data and failures to replicate results. The debate continues in scientific journals, with new papers appearing regularly on both sides. What makes this debate relevant to our inquiry is its implications. If a cosmic impact triggered the Younger Dryas, it would represent a catastrophic event that profoundly affected human populations. It would provide a mechanism for the kind of sudden civilization-ending disaster that appears in mythology around the world. The timing is suggestive. The Younger Dryas began roughly 12,800 years ago. This is precisely the period when the great megafauna of North America went extinct. Mammoths, mastodons, giant ground sloths, dire wolves, saber-toothed cats, and dozens of other species vanished within a geological instant. The Clovis culture, the first well-documented human population in North America, disappeared at almost exactly the same time. The conventional explanation for these extinctions involves human hunting and climate change. As humans spread across North America, they hunted the naive megafauna to extinction. As the climate fluctuated, habitats shifted, and species that could not adapt died out. These explanations have merit, and they almost certainly played a role. But the sheer rapidity and synchronicity of the extinctions has puzzled scientists for decades. A cosmic impact could explain the pattern. A catastrophic event that killed animals directly through blast and fire, indirectly through climate disruption, and triggered a cascade of ecological collapse. The impact would not need to cause all the extinctions directly. It would just need to push ecosystems that were already stressed over the edge. In recent years, new evidence has emerged from unexpected sources. Researchers analyzing sediment cores from Baffin Bay near Greenland reported finding metallic debris in microspherules consistent with a cosmic impact at the Younger Dryas boundary. This was the first time impact-related materials had been found in marine sediments. Adding to the evidence from terrestrial sites, the debate is not settled. Many geologists and paleontologists remain skeptical. They point out that no crater has been found, no smoking gun that would definitively prove an impact. The evidence is circumstantial, they argue, and could be explained by other processes. But the absence of a crater is not necessarily damning. If the impactor struck the ice sheet covering North America, any crater would have been erased as the ice melted. If the comet fragmented and produced multiple airbursts rather than a single ground impact, there would be no crater to find. The Tunguska event in Siberia in 1908 flattened 2,000 square kilometers of forest without leaving a crater because the object exploded in the atmosphere before reaching the ground. What matters for our inquiry is not whether the Younger Dryas impact hypothesis is correct. What matters is what the hypothesis illustrates about the vulnerability of civilizations and the potential for catastrophic discontinuities in history. Consider the scenario. 12,800 years ago, humans had been living in the Americas for at least 1,000 years, possibly much longer. They had developed sophisticated stone tool technologies. They had spread across 2 continents. They were beginning to settle in larger groups and experiment with new ways of life. The site of Abu Huraira in Syria shows evidence that people were beginning to cultivate wild cereals right around this time. Then disaster struck. Whether through climate change alone or climate change triggered by cosmic impact, the world transformed rapidly. Temperatures plunged, food sources disappeared, populations crashed. The cultural continuity that allowed knowledge to be passed from generation to generation was broken. This is exactly the kind of event that could erase the memory of what came before. A catastrophe severe enough to kill most of the population and disrupt the social structures that preserve knowledge would create a discontinuity in the historical record. Survivors would retain some skills and stories, but much would be lost. Subsequent generations would remember only fragments, distorted by time and retelling. The Younger Dryas was not so severe that it ended humanity. People survived. Some populations may have even thrived as competitors disappeared, but it was severe enough to cause major disruption, to end cultures, to extinguish knowledge. If something like this happened multiple times over the hundreds of thousands of years of human existence, the cumulative loss of knowledge could be immense. Each catastrophe would create a gap. Each gap would widen as survivors struggled to recover and rebuild. The deep past would become increasingly inaccessible, not because nothing happened, but because the links that connected it to the present were severed. The Younger Dryas reminds us that history is not a smooth progression. It is punctuated by crises, by catastrophes, by moments when everything changes. These moments can erase centuries of progress, can scatter populations and destroy cultures, can create gaps in the record that can never be filled. We emerged from the Younger Dryas. The climate warmed again. Agriculture developed. Cities arose. Civilizations flourished. We built the world we know today. But we should not assume that our path from the Ice Age to the present was the only possible path, or that nothing was lost along the way. The Younger Dryas stands as a warning, a reminder that the past is fragile, that knowledge can be destroyed, that catastrophe can strike without warning. And perhaps, buried in the sediments from that terrible time, there are secrets still waiting to be found. Chapter 9. The Silence in the Stone. We have traveled through deep time together. We have examined the geological processes that erase evidence, the climatic events that resemble industrial signatures, The myths that preserve fragments of memory. The archaeological surprises that remind us how much we do not know. Now we must confront the most important question directly. What does the silence in the stone actually tell us? The geological record does not contain evidence of previous industrial civilizations. No fossilized machines, no ancient reactors, no cities preserved in rock, no synthetic materials embedded in sediment older than a few decades. The record is, by any reasonable standard, silent. This silence is the strongest argument against the existence of previous civilizations. If someone had been here before, if they had built and burned and manufactured on any significant scale, we should find traces. We do not. But the Silurian Hypothesis asks us to examine this silence more carefully, to understand not just what the record says, but what it is capable of saying, to distinguish between absence of evidence and evidence of absence. Let us consider what would actually survive from our own civilization after 50 million years. The radioactive signature from nuclear weapons testing would persist. Isotopes like plutonium-239 and cesium-137 would decay over thousands of years, but their decay products would remain, creating anomalies detectable with sensitive instruments. This is probably our most durable marker. The carbon isotope excursion from burning fossil fuels would be preserved in marine sediment. Future geologists would see a rapid shift in the ratio of carbon-12 to carbon-13, indicating a massive release of organic carbon into the atmosphere. This signature could persist for millions of years. The mass extinction we are causing would appear in the fossil record as a sudden collapse of biodiversity, followed by the expansion of weedy generalist species. This pattern would be recognizable for tens or hundreds of millions of years. Synthetic chemicals might leave traces. Certain plastics and industrial compounds could persist in sediment long enough to be detectable. But the further back in time you go, the harder these would be to distinguish from naturally occurring organic compounds. Physical artifacts would be essentially gone. Erosion, burial, metamorphism, and subduction would destroy any structures or objects within a few million years at most. The steel and concrete and glass that define our world would leave no recognizable trace. Now project this backward. If a civilization existed 50 million years ago and left similar traces, what would we find? The radioactive signature would be long gone. Plutonium-239 has a half-life of 24,000 years. After 50 million years, not a single atom would remain. Even longer-lived isotopes would be undetectable. The carbon isotope anomaly might still be visible, depending on how well preserved the sediments are, but it would be compressed into a thin layer that could easily be confused with natural events like volcanic carbon release or methane hydrate destabilization. The extinction signature would be harder to interpret the further back in time you go. The fossil record becomes sparser and more fragmentary with age. Distinguishing between an extinction caused by a civilization and one caused by climate change or asteroid impact would be extremely difficult. Synthetic compounds would be degraded beyond recognition. The complex polymers that characterize our industrial output break down over time into simpler molecules that could have multiple origins. Physical artifacts would be entirely absent, not because they never existed, but because the Earth would have destroyed them completely. The uncomfortable conclusion is that a civilization similar to our own, if it existed 50 million years ago, would leave traces that are difficult or impossible to distinguish from natural processes. We would see anomalies in the record, but we would not know what caused them. We would likely attribute them to volcanoes or asteroid impacts or climate feedbacks, because those are the explanations our methods are designed to find. This does not mean such a civilization existed. It means we cannot be certain it did not. There are, however, arguments that push back against this uncertainty. First, the presence of easily accessible resources. When humans began industrializing, we found coal and oil and natural gas in abundance. These fossil fuels had accumulated over hundreds of millions of years. If a previous civilization had extracted and burned them, we would expect to find depleted deposits, evidence of prior exploitation. The fact that these resources were waiting for us suggests no one had used them before. This is a strong argument, but it has limits. A civilization that arose before the Carboniferous period, before the great forests that became coal even existed, would have had no fossil fuels to exploit. A civilization that developed different energy technologies, perhaps based on solar or geothermal or nuclear power, might have left fossil fuels untouched. Second, the absence of technosignatures in the broader solar system. If a previous civilization achieved spaceflight, they might have left artifacts on the Moon or Mars, where erosion and tectonic activity are minimal. We have surveyed these bodies and found nothing artificial. This is evidence, though not proof, that no spacefaring civilization preceded us. Again, this argument has limits. We have examined only a tiny fraction of the solar system's surface. Small artifacts would be invisible to our instruments, and not every civilization necessarily develops spaceflight. Ours has existed for only 300 years and has placed only a handful of objects on other worlds. Third, the fossil record of intelligent species. We know that humans evolved from primate ancestors over millions of years. We can trace our lineage through the fossil record. If another intelligent species had evolved and built a civilization, we might expect to find some trace of them in the fossil record as well. But fossilization is rare, and intelligence is not necessarily associated with physical features that preserve well. We recognize human ancestors by their bones and stone tools, but a species that did not make stone tools, or whose tools were made of perishable materials, might leave no trace at all. The silence in the stone is real. It tells us that no civilization has left obvious, unmistakable evidence of its existence in the deep past. It tells us that if previous civilizations existed, they were either very different from us or very unlucky in their preservation. But the silence does not tell us that previous civilizations definitely did not exist. It tells us that we cannot know for certain. This uncertainty is uncomfortable. We are used to thinking of science as providing answers, not highlighting the limits of knowledge. But honest science acknowledges what it does not know. And what we do not know about the deep past is vast. Frank and Schmidt in their original paper were careful to emphasize that they strongly doubt any previous industrial civilization existed. The weight of evidence is against it. The silence in the stone, while not conclusive, is suggestive. The most parsimonious explanation is that we are alone in Earth's history. But they also noted that asking the question is valuable, regardless of the answer. The Silurian hypothesis forces us to think about what evidence would look like, about how long it would last, about what methods would be needed to detect it. This kind of thinking has implications far beyond Earth. We are searching for signs of life on other planets. We are scanning distant stars for radio signals from alien civilizations. We are examining the atmospheres of exoplanets for biosignatures. These searches assume we know what we are looking for. They assume we can distinguish between natural processes and technological activity. The Silurian hypothesis suggests we should be humble about these assumptions. If we cannot be certain about the deep past of our own planet, how can we be confident about detecting civilizations light years away? The silence we find in distant systems might reflect not the absence of life, but the limits of our detection methods. The stone is silent, but silence has many meanings. It can mean that nothing was ever said. It can mean that words were spoken and forgotten. It can mean that we are not listening correctly. The deep past of our planet remains largely unknown. Most of what has occurred here is lost forever. The silence in the stone is not an answer. It is a question that cannot be fully resolved. We are probably alone in Earth's history. The evidence points that way. But probably is not certainly. And the margin of uncertainty, however small, reminds us that the universe is stranger and more mysterious than we can imagine. The silence speaks if we learn to listen, and what it says is that we do not know everything. We never will. Chapter 10. What we will leave behind. We have asked whether civilizations came before us. Now let us ask what will remain of us. What will future observers, whether human or otherwise, find in the geological record millions of years from now? What story will the rocks tell about who we were and what we did? The answer is sobering. We are writing ourselves into the stone in ways that will persist for ages. But the story the stone tells may not be the one we would choose to leave behind. The most distinctive marker of our era is the mass extinction we are causing. Species are disappearing at rates 100 to 1,000 times higher than the natural background rate. The International Union for Conservation of Nature lists over 40,000 species as threatened with extinction. Amphibians, birds, mammals, fish, insects, and plants are all declining. The web of life that has existed for millions of years is being torn apart. This extinction will appear in the fossil record as a sharp boundary. Below the boundary, diverse ecosystems with many species. Above it, impoverished communities dominated by a handful of generalists. Rats, cockroaches, crows. Species that thrive in disturbed environments. Species that can coexist with humans. Future paleontologists will recognize this boundary. They will see it as we see the Cretaceous-Paleogene boundary that marks the extinction of the dinosaurs. They will know that something catastrophic happened at this moment in Earth's history. They will see the collapse of biodiversity and search for the cause. The cause will be written in the chemistry of the sediment, a spike in carbon isotopes indicating massive release of fossil carbon, elevated concentrations of nitrogen from agricultural fertilizers, heavy metals from industrial processes, plastics and synthetic chemicals that have no natural origin, radioactive isotopes from nuclear weapons testing. These signatures will tell a story, a species that discovered how to unlock the energy stored in ancient carbon, a species that transformed the composition of the atmosphere, the chemistry of the oceans, the surface of the land, a species that spread across the globe and remade the world in its image. For a brief moment, perhaps a few centuries, perhaps a few millennia, this species dominated. It extracted resources, built structures, generated waste. It altered the climate, acidified the oceans, and drove countless other species to extinction. It left behind a layer of synthetic materials, a spike of radioactive isotopes, a collapse of biodiversity, and then it was gone. Or perhaps it persisted in some form, adapting to the world it had created. But the world it had created was not the world it had found. The damage was done. The evidence was preserved in stone. This is what we are leaving behind. Not a story of triumph or progress. A story of impact, of disruption, of change so rapid that the geological record will show it as an instant. A boundary, a discontinuity. Scientists have proposed calling this period the Anthropocene, the age of humans. The term captures something important. We are no longer merely inhabitants of the Earth. We are a force of nature, comparable in our effects to volcanic eruptions and asteroid impacts. We are writing our own chapter in the geological record, but the chapter we are writing is not flattering. Future observers, if there are any, will see us the way we see the asteroid that killed the dinosaurs. As a catastrophe, as a force of destruction, as a cause of mass extinction. We do not intend to be remembered this way. We think of ourselves as creators, as builders, as the species that produced art and music and literature and science. We imagine that our achievements will be remembered, our monuments preserved, our knowledge passed on. But the geological record does not preserve achievements. It preserves impacts. The asteroid did not intend to kill the dinosaurs. It was not evil. It simply collided with the planet, and the consequences followed. We do not intend to cause a mass extinction either. But our intentions do not matter. The consequences are what they are. There is perhaps a different story that could be told. A story of a species that recognized its impact and changed course. A story of wisdom rather than destruction. A story of sustainability rather than exploitation. A story that future observers might read not as a warning, but as an example. This story is still being written. The outcome is not determined. We have the knowledge to understand what we are doing, and the technology to do things differently. Whether we will choose a different path remains to be seen. But time is short. The carbon is already in the atmosphere. The species are already extinct. The plastics are already in the ocean. The radioactive isotopes are already in the sediment. Whatever choices we make now, the record of what we have already done is permanent. It will outlast our cities, our monuments, our civilizations. It will be readable in the rocks for millions of years after the last human is gone. We began this journey by asking whether we are the first civilization on this planet. The evidence suggests that we probably are. The geological record contains no unmistakable traces of industrial activity before our own. The silence in the stone is consistent with the hypothesis that we are alone in Earth's history. But this conclusion should not bring comfort. If we are the first, we are also setting the template. We are showing what a technological civilization does to a planet. We are demonstrating the trajectory from emergence to impact, to either extinction or transformation. If there are other technological civilizations in the universe, their observers might look at planets like Earth and wonder whether any have produced intelligent life. They might scan for biosignatures and technosignatures, looking for evidence of activity. They might find the chemical traces we are leaving now and recognize them as the fingerprints of a species like themselves. Or they might find only silence, the aftermath of a species that burned too bright and too fast, that consumed its world and vanished, leaving behind only a thin layer of anomalies in the rock, a cautionary tale encoded in stone. The Silurian Hypothesis began as a thought experiment, a way of testing the limits of our detection methods. But it has deeper implications. It asks us to think about our place in time, about the permanence of our achievements, about what we want to leave behind. We are temporary. Our individual lives last decades. Our civilizations last centuries or millennia. Even our species will eventually be gone, replaced by whatever comes next, or simply extinct. The Earth has seen countless species rise and fall. We are neither the first nor the last. But we are here now. We have the ability to choose. We can continue on our current path and leave behind a record of destruction. Or we can change course and leave behind a different kind of evidence. A species that learned. A species that adapted. A species that found a way to persist. The choice is ours. The stone is waiting. What story will we write? If you have enjoyed this deep investigation into the deep past and the questions it raises about our own civilization, please like this video and subscribe to the channel. Your support makes these detailed explorations possible. Tell me in the comments what you think. Are we alone in Earth's history? What evidence would convince you otherwise? And what story do you think we will leave behind for future observers to find? The past is vast and mostly lost. The future is uncertain, but the present is ours. And the choices we make today will echo in the rocks for millions of years. Thank you for watching.